and we are into 8.2, products and quotients of functions. So we learned that you can add and subtract functions, but you can also multiply and divide functions. We've seen some of that. Multiplying functions, an example of that is just expanding two binomials. You could have two functions. You're multiplying two polynomials together would be an example, but that's just using polynomials. Now we have a variety of different types of functions that we're working with, and a quotient, dividing one polynomial by another polynomial, we've done in rational functions, but now in this case you could have a different type of function that you're dividing by. So at the top of the page you have a little bit of space for notes, and the first note that we're going to take is we can simplify a combined function. We can simplify a combined function formed by the product or quotient of functions. So we can simplify a combined function formed by the product or quotient of functions, so two or more functions, by using previously learned algebra skills. What that's saying is that most of the rules that we already know about multiplying and dividing using variables in algebra will apply to combining functions in this way as well. So we basically just jump right in and see a bunch of different types of things here. So we're in example 1. And example 1a says, for the whole example, I'll just type out what f of x is. F of x is x plus 3, and g of x is x squared plus 8x plus 15. So those are our two functions, and in A, we're going to create the product of these two functions. So we're going to create y equals f of x, g of x, or f of x times g of x. And you'd set that up pretty much how you would think to. You just bracket f of x, which is the binomial x plus 3, and then bracket the x squared plus 8x plus 15, and we know there's multiplication implied between them. And then we distribute, okay? The challenge here is you can't really use FOIL because there are more than two terms in the second polynomial. There's a trinomial. You do need to make sure that every single piece of the first binomial is multiplied by every single piece of the second polynomial there. So we're going to end up with 6 terms that we can then group like terms. So first, I'm going to deal with all of them multiplied by this x, the first term in the binomial. So we've got x times x squared, that's x cubed, plus 8x squared plus 15x. Now I'm working with the 3. We've got plus 3x plus 24x plus 45. That one was pretty straightforward because there are no negatives there, so I didn't have to worry about signs and things like that. In order to combine like terms or group like terms, I actually made an error. I should have 3x squared here. I don't know if I said that, but I didn't write it. To group like terms, sometimes I like to just underline them using different types of underlines. And then in order from greatest power, highest order of x, and decreasing, we've got x cubed, then we have 8x squared plus 3x squared, which is 11x squared. 15x plus 24x, that's 39x's, and a constant of 45. So that's an equation for the combined function. And if we wanted to graph this, which we're asked to do, we're going to sketch a graph of it. The most helpful form is actually starting here with what we wrote at first, because it's already factored out an x plus 3. So we're kind of reaching back into how to sketch a graph of polynomial. You would have to find the first factor, then you'd have to divide this polynomial by the first factor, using all of those, what is it, like the zero product rule and integral zero rule, things like that.
You can factor the quadratic part. Then we get x plus 3 and x plus 5.
Nice.
Then
So
x plus 3 squared times x plus 5.
Yeah. So to sketch it, we're going to factor completely, which I'm just going to pull this guy over here. And that's exactly right. We just need to factor the x squared plus 8x plus 15. So looking for two numbers that multiply to 15 and add to 8, that's 5 and 3. So we end up with x plus 3 times x plus 3 times x plus 5. And in order to know how to sketch this, I'd want to go with x plus 3 squared here. And if we're remembering back, so I told you this unit was a lot of review, but if you're remembering back, you know that if I have a polynomial, I have a 0 of -3 here, but it's a 0 of order 2, which tells me how the curve interacts with the x-axis at the point -3. So it's going to cross at x equals -5, but at x equals -3, it's just going to touch. It's not going to change its sign. Okay? We should make a note of that. Zeros of x equals -3. Then in brackets, that's order 2. And x equals -5. And if it's order 1, you don't really need to say anything specifically. So that gives our x-intercepts. So down at the bottom, I think you guys have a little graph already ready to go. Okay, if it doesn't have its axes, then this is kind of what they should look like. Don't put them right in the middle. You might run out of space. Got our y-axis and our x-axis. And we're going to go -1, 2, 3, 4, 5. And our y-axis is going to move a little bit differently. We know that we have a y-intercept at +45. So I'm just going to go maybe 10, 20, 30, 40. I have the benefit of using whiteboard marker. So here's my going to be 45 for me. And what do I know about this graph? Well, it's positive and it's cubic. So I'm starting down here in Q3 and ending in quadrant 1. So at the least I know I'm going up like this to start, and I'm going to end going up like this. And in the meantime, I'm going to cross at x equals -5 and then dip back down and touch at x equals -3. So 1, 2, 3. I'm going to touch there. I'm going to cross here. So it's going to look something like this. And then I'm going to have to hit my y-intercept of 45. And again, if you graphed this on Desmos, it would probably look a little bit different because our scale, my x and y scales are different. My x goes down by 1, whereas my y's go up by 10s. But there we have a rough sketch of what it would look like. And then we talk about restrictions, state its domain and range. Because these two, f of x and g of x, are just regular polynomials, there are no restrictions on them. Okay, domain and range. I can put in any value of x into either of them for the domain, and the range there is a restriction on the range of this quadratic of g of x, but not on the combined function. Okay, so because there are no restrictions on the domain of the original two functions, there are no restrictions on x and y. The domain is x belongs to the set of real numbers, range y belongs to the set of real numbers. All right, example 1b, we're working with the same f of x and g of x, but this time we're looking at y equals f of x over g of x. Okay, so now we go back into all that we know about our rational functions. We've got one polynomial over another polynomial. First thing I'm going to do is just sub them in. I've got x plus 3 in the numerator, and my denominator is x squared plus 8x plus 15. So again, we're reviewing how to work with rational functions. The first thing I want to do is simplify this, and I don't even know that I can. When you're simplifying fractions, it's okay, can I reduce this into lowest terms? And I can't tell right now. We already factored the denominator, so we know what we're going to end up with. But that's always the next step, is going to be factor the denominator. Factor denominator. If you're working with rational functions and you don't think you know what to do, factor the denominator and then reevaluate. So my numerator is still x plus 3. We already factored the denominator. We know it's x plus 3 times x plus 5. And now all of a sudden I have a common factor in the numerator and the denominator, which I can cancel out. What do I need to remember though as I move on to my next step? Something about denominators and variables.
Well, it's a rational function now. It's 1 over x plus 5.
Okay, so it's simplified to 1 over x plus 5, but if I wrote that as a final answer and I graphed it, I would get it slightly incorrect.
There is a restriction.
There's a restriction.
-5.
Okay, so the one restriction that x can't be -5 is really obvious. It's there, but there's another restriction.
Can't be -3.
X can't be -3. Okay, anytime that the variable or a factor is in the denominator, we need to carry that through. So basically the function will look like 1 over x plus 5, but there will be a gap at x equals -3. Good. And we can draw that. The best way to draw that is to think of the basic parent function, which is 1 over x. So the parent function 1 over x looks like this. Has one leg in Q1 and one leg in Q3. And what we're doing is applying a horizontal translation 5 units to the left. So 1, 2, 3, 4, 5. I could give myself an asymptote there, a vertical asymptote. Haven't moved this thing up or down. I'm just moving the whole thing 5 units to the left, so my new one is going to have the exact same shape, but it's going to be hugging that new asymptote, extending to -infinity and +infinity. And we can name our graphs here while we're here. Y equals 1 over x plus 5. And our red graph was y equals 1 over x. And then we also want to make sure that we have added our whole, which is at x equals -3. But I want to, you could also maybe find out the y value that goes with it if you needed to know the coordinates of that whole. Let's just do it to find the coordinates of the whole. You just plug x equals -3 into your equation. So the y value that goes with the x value of -3 is 1/2, which gives you a gap at -3, 1/2. It's just called a discontinuity in the graph. But it also helps us because we need it in order to do the domain and range. So our domain here, we have 2 restrictions on the domain. We know x belongs to the set of real numbers, but x can't be -3. That's where our gap is, and x can't be -5. That's where our asymptote is. For our range, y belongs to the set of real numbers, such that y, we just figured out, can't be 1/2. 1/2, and y can't be 0. So we have a horizontal asymptote there. And it's all the information that we needed. Okay, in the next example, we apply it to a long word problem. And it's baseball marketing. In an effort to boost fan support, the owners of a baseball team have agreed to gradually reduce ticket prices. So ticket prices are going down in dollars according to the function P of G, so price per game, is equal to 25 minus 0.1 G, where G is the number of games that have been played so far this season. So the first game, your ticket's going to be $25. For the next game, it's going to be $24.90. For the next game, it's going to be $24.80. And that's how he's boosting fan support, keeping the fans interested throughout the season. The owners are also randomly giving away free baseball caps. The number of baseball caps that they give away is C in hundreds. So we get C hundreds of caps given away per game. It's modeled by 2 minus 0.04 G. Okay? And again, that number is going to be multiplied by 100. Since these marketing initiatives began, the number in hundreds of fans in attendance has been modeled by the function N, number of fans, with respect to G, the number of games, is equal to 10 plus 0.2 G. So just from looking at that, it kind of seems like his plan is working. But we're going to find out that there's kind of a sweet spot that he wants to be in. There's a certain number of games in the season that this works for, and if your season is longer, then it stops being effective on your fans. So what we're going to do is develop an algebraic and graphical model for f of g, which is being given as p of g times n of g. So that's the price. You can actually, let's write it down and we'll talk about what it means. So in A, we have f of g equals p of g times n of g. So this new function is the product of two functions, and it's the price per game, price per ticket, ticket price, times the number of people in attendance. So what is this figure? What does f of g represent? What's happening? Like, we're talking about money, we're talking about games, we're talking about hats. If I take the price of each ticket and the number of people, what does this mean for the owner of the team?
Price times how many people are buying tickets.
So what, do you know the word for that in the business world?
Revenue?
Revenue. It's all the money coming in. Revenue from ticket sales. Well, let's develop an algebraic model. So we're just going to sub in P of G, which is given as 25 minus 0.1 G, and N of G, which is given as 10 plus 0.2 G. And we expand that. So now I have two binomials, the product of two binomials, so I can FOIL that. I get first times first, 25 times 10 is 250. 25 times 0.2 G is basically take 25 and divide it by 5. It's 5G. Then I have inside times inside, which is going to be negative 1G. And last times last, which is going to be negative 0.02G squared. 2 times 1 is 2, 2 decimal places, and 2 factors of G. I'm going to rearrange this so it's in descending powers of x. We've got negative 0.02G squared plus 4G plus 250. And we're going to draw a quick sketch of this. It's a parabola. It's really wide. It opens down. We could figure out where it reaches its max, but we're not going to. It's only relevant for G greater than 0. And it's going to look something like make it look a bit more parabola-y. And I'm just making a mess of it. That is f of g, which is the product of p of g times n of g. And we know some of the values. We know this is 250. And I'll just give you some of the other ones. The vertex happens at 90 games. So you could split that in half. That's 135. That would make this maybe 200, 100-ish. And our max revenue ends up being up here at 450. Okay, you could figure that all out by taking this and putting it in vertex form to get your maximum revenue and the number of games that it happens at. But this isn't the only factor. He's also giving away a certain number of hats. And so I guess the answer to this is applying this strategy, price per ticket, is that going to have a positive or negative effect on their sales?
Well, they need a lot of games for it to have a negative effect. So
Yeah, it's mostly positive, right? Hockey has 82 games. If it's baseball, which it is, the MLB has 162 games. So actually for them, they come out pretty much even.
well, this is for a team though, not
Each team in a season in baseball will play 162 games, which is insane. But they do. Football, they only play, what, 18 weeks? 16 weeks? Something like that. Anyway, 16 weeks, I think. Moving on to B. So it's short term, it's a really good plan. Long term, it's not looking so great. B says, develop an algebraic model for f of g equals c of g over n of g. So B is f of g equals c of g over n of g and explain what it means. So C of g is the number of caps being given away, and n of g is the number of people. And if you look at C of g, the number of caps given away per game, is that going up per game or down per game?
It's going down.
There are fewer caps every game. What about the number of people, more or less each game?
It's more.
More each game. So when are your best odds of getting a free hat at a game? Earlier in the season or later in the season?
End of the season.
If the number of caps is going down and the number of people is going up, then as the season goes on, your odds of getting a cap are less and less and less. So there are fewer caps and more people, right? You would be better off with fewer people and more caps. At any rate, what we are tasked with is finding how likely are you to receive a baseball cap if you attend Game 5, a free baseball cap, that is. So we just take our formulas that we have, C of g, which is 2 minus 0.04 g, and over n of g, which is 10 plus 0.2 g. And we can divide this out. We could graph it. I'll just graph it quick. The graph kind of looks like this. You might be able to factor something out here and make it easier on yourself, but so it's kind of a curve that looks like that. That's one side of the curve. It's a rational function, so the whole thing isn't useful because g can't be less than 0, right? So there's another leg somewhere over here doing something else. That's kind of what it looks like. We don't need to know that too much. We came up with our function, our combined function, our quotient of two functions. And then we're just going to sub in 5 for g and figure out what the odds are. So f of 5 means if you went to the 5th game, the number of caps would be represented by 2 minus 0.04 times 5. And the number of people is 10 plus 0.2 times 5. We're also keeping in mind that both of these numbers are given in hundreds. The number of people in hundreds and the caps in hundreds. If only one of them was given in hundreds, we'd have to multiply it by 100 before starting. Okay, but they are both given in hundreds. So it's essentially like the numerator and the denominator have been divided by 100, which is fair. Okay, here we get 2 minus 0.2, which is 1.8. And in the denominator, we get 10 plus 1, which is 11. And we'd put that in the calculator, and we would get approximately, oh, not approximately, it's a repeated decimal, so we get 0.163 repeating. What does this tell us?
You have a 16 or 33% chance.
Yeah. So you've got about a 16% chance of getting a hat in Game 5. Of getting a free hat if you attend Game 5. It's somewhat real-world situation. Can you think of any other factors that would affect your chance of getting a free hat? If you're in the loudest section, you're probably more likely to get a hat because they'll shoot the hats that way.
Like your seat?
Your seat, how far you are from where they're shooting the hats. What about how tall you are or how obnoxious you are? That'll have an
Did
effect.
you see that clip of Jake when